Dabar aš nežinau, kiek jūs esat kosmose pasidomėję. Yra toks dalykas kaip Boots Void, aš nežinau, kaip čia tarti realiai teisingai reikia. Bet, yra teorija dabar, tarkim, mūsų, vėlgi, aš čia turbūt 100 dalykų net visai teisingai pasakysiu, bet paskui porą video gal pažiūrėsim. Taip kaip mes matom visatą, mes matom tiek, kiek šviesa mums leidžia matyti. Visata plečiasi, mes tą kaip ir nustatėm, pamatavom, nesuprantam, kodėl greičiau plečiasi tolimesni dalykai, lėčiau artimesni atrodo gal, ir tas ekspansas akceleruoja, kiti sako, kad visur vienu metu taip pat. Žodžiu, daug neatskaitų klausimų. Ir yra tokie dalykai tada kaip Boots Void, kur realiai mūsų tam Observable Universe atrodo tokios ne tik, kad visai tuščios vietos, bet kosmoso skaliai kaip ir tuščios vietos, kur tų galaktikų nėra. Kas irgi nelabai supranta, kaip paaiškinti ko. Žodžiu, kažkur šitam visam modelį atsirado Dark Matter, Dark Energy, man atrodo. Žodžiu, kad paaiškinti matematiškai, kaip apskritai veikia tas expansas šitos mūsų visos visatos, I guess. Dabar, James Webb teleskopas nesenai atrado dalyką, kur dabar visi apie tai video daro ir ką mes pažiūrėsim, kad pasirodo dabar, ir ten darbas išėjo parašytas, aš nežinau ten koks tiksliai, nes aš nežinau, kur rasti reiktų, bet nuo to visi video prasidėjo, kad James Webb teleskopas realiai ir mokslininkai biški naują modelį kaip ir padarė, kuris daug geriau tinka observationams, nes kaip suprantu, James Webb teleskopas, kai žiūrėjo labai tas tolimas galaktikas, nematė to, ko numatytų tas senasis modelis. Tai, mokslininkai kaip ir šitas modelis matomai kažkas čia negerai, kažkas neveikia. Tai kaip suprantu, iš nuogirdų, vieno kito ten, kad dabar naują modelį padarė, kur realiai tas Dark Matter ar Dark Energy net nereikalingas yra, kad paaiškint dalykus. Ir viena iš tų teorijų tokių yra, kaip jin vadinasi, aš dabar pamiršau, toj mes pažiūrėsim ir bent jau išgirsim tą pavadinimą, kad mes realiai, mūsų galaktika yra viename iš tų voidų. Tai man atrodo, čia yra keletas video, man atrodo, reikia pažiūrėti šitą, norėjau pažiūrėti. Jo, pradėsim tiesiog nuo šito, čia bus keli trumpi tokie video, kur gal bišk paaiškins, nes šiaip gan exciting dalykai ir čia yra visiška magija, gerai. Kiek magija gali egzistuoti mums dabar, ant kiek mes nesuprantam ir nepaaiškinam ir absurdiška.
Outer space. The nothing in between the something actually has different classifications. Interplanetary space. This is the space within the confines of a solar system, defined by the solar wind from the sun. But space reaches further. Interstellar space. This is the space in between solar systems beyond reach of any bubbles of plasma, being under the reign of only the black hole at the center of the galaxy. While that might sound dreadful, there's another terrifying classification of nothing. Intergalactic space. The space in between galaxies. This is what makes up about 90% of the universe, and the interesting thing is this empty space seems to be inconsistent and fluctuant. We can see this in instances like the Boötes Void, or more commonly known as the Great Nothing. A spherical space spanning around 330 million light years in diameter, or 10 septillion, 526 sextillion, 629 quintillion, 999 quadrillion, 999 trillion, 999 billion, 348 million, 310,016 bananas, all lined up. Okay. Within the massive volume of the Great Nothing, you could normally expect to see thousands of galaxies, but the Boötes Void only has about 60. To give you a better idea of how empty that really is, we discovered other galaxies.
Ja, beveik kiek Rusinas norėjo iš Google prisiteisti, true.
The Andromeda Galaxy in 1925. We discovered 60. To give you a better idea of how empty that really is, we discovered other galaxies, the Andromeda Galaxy, in 1923. But if you were to place our galaxy, the Milky Way, into the middle of the Boötes void, we wouldn't have even known there were other galaxies in the universe until about the 1960s. So why does this gap in space exist? To answer that question, we must first have a surface understanding of the nature of the universe. The universe is a sponge. Galaxies group into clusters. The Milky Way, for example, is a part of the Virgo cluster. But if you zoom out, you'd see that even clusters form into superclusters. Our Virgo cluster being a part of the Lyapunina supercluster. These superclusters have giant voids of their own, but if we zoom out one more time, we see these massive voids in between superclusters, the biggest being the Boötes void. Cool. So why does the matter cluster up, forming these huge voids? The short, confusing answer is that we think it's because of various fluctuations just after the Big Bang that have evolved and expanded over 13.8 billion years to leave a much lower density of materials than the areas around it. Blah, blah, blah. Long answer is easier to understand, but a little more complex. Let's go back to the Big Bang, or more specifically, 10 to the minus 32 seconds after the Big Bang. At this point, the visible universe is quite small. And when I say quite small, I mean incomprehensibly small. At this scale, you'd end up with quantum fluctuations of space-time, which is a lot of words that I barely even know, so let's break it down. Look at the air around you, but zoom in really, really close to the space in between the atoms. You'll see energy spawning in and out of existence randomly, called quantum fluctuations. But they are so small that they don't really do anything or affect anything. But when the entire observable universe is that small, you best believe that the random spawnings of energy is going to interfere with stuff. You end up with interactions between really simple matter in the universe and light trapped in it being completely confined. These interactions cause oscillations, or in other words, the universe was playing Pong with photons. And the universe continues to play Pong for about 380,000 years when the recombination happens, or basically, the kind of stuff becomes real stuff, the universe forms its first atoms, and because of this, the light is not bouncing around in all that kind of stuff, and is free to expand out indefinitely into the universe. And so is everything else. Hence the ever-expanding universe. And we actually have a picture of that very moment called the cosmic microwave background, or in other words, the fingerprint of the universe. It's a picture of the microwave radiation that fills all of space in the observable universe. Notice how there's random fluctuations in radiation. This is exactly what it was like when things were first let loose and started to expand, which is why everything is clumped up. Because it started that way from random quantum fluctuation, and the space in between is only getting bigger to the unstoppable expansion of the universe. Look on the bright side. There's a really big gap, and that's pretty cool.
Okay. Tai čia labai trumpai papasakojom maždaug šitą ir tada, man atrodo, šitas darbo video. Aš neįsivaizduoju, kiek...
Get ready to be amazed, because...
Čia skamba kaip AI balsas. Aš neįsivaizduoju, kiek patikima yra šitie duomenys, tai šiek tiek pažiūrėsim ir tada, man atrodo, dar pažiūrėsim vieną, kur kalbėjo žmogus, kur actually nusimano šitose temose ir jo, mes pažiūrėsim video, nes šita teorija, kaip suprantu, yra labai įdomi. Tai jo, šitas, man atrodo, video, davai.
Get ready to be amazed, because recent discoveries about the universe are set to challenge everything we thought we knew. Scientists are now questioning the idea that the universe has a definite age and are rethinking the role of dark energy in its accelerating expansion. Instead, they believe something even more mysterious is at play. Groundbreaking observations from the James Webb Space Telescope are uncovering strange and unexpected secrets of the cosmos. The astonishing structures captured in Webb's latest images have left astronomers around the world stunned, reshaping our understanding of the universe itself.
I don't believe in any religion I've seen. So in that sense, I'm an atheist. However, I would say that there is something going on which might resonate with a religious perspective.
A few months ago, some of the world's leading cosmologists met at the Royal Society in London to ask the question, what if our fundamental assumptions about the universe are wrong? The meeting was held because many high-level astronomical observations have challenged the traditional cosmological model, according to Professor Subir Sarkar, a cosmologist at the University of Oxford and co-organizer of the meeting, we are, in cosmology, using a model that was first formulated in 1922. We have great data, but the theoretical basis is past its sell-by date. More and more people are saying the same thing, and these are respected astronomers. What he really wants to say is that for centuries, people thought the universe was static or unchanging. But in the 20th century, scientists discovered that the universe is actually expanding. Galaxies are moving away from each other. The big question was whether this expansion would slow down over time because of gravity pulling everything back together. Now, here's where things got surprising. When scientists studied distant exploding stars, which provided a more reliable way to measure how the universe is expanding, they expected to find that the expansion was slowing down over time, similar to how a ball thrown into the air slows down as gravity pulls it back. Instead, they found the opposite. The universe's expansion was speeding up. This discovery shocked everyone and completely changed how we think about the universe. To explain it, scientists propose that a mysterious force called dark energy is pushing galaxies apart, working against gravity. Dark energy makes up about 70% of the universe and is still one of the biggest mysteries in science. All of this comes together along with ordinary matter to form what we call the lambda cold dark matter model. And using this expanding universe model, scientists have also found out the age of the universe. It's like rewinding the clock. If the universe is expanding now, scientists calculate how long it would take to shrink everything back to a single point, and they discovered that the universe is about 13.8 billion years old. But the problem is that this model uses a simplified equation that assumes the whole universe is smooth and expands at the same speed everywhere. But on the other hand, new images from the Webb telescope revealed large galactic filament structures separated by vast voids emptier than we can comprehend. Also, previous observations of 1.5 million quasars showed that there are about 0.5% more quasars on one side of the sky than on the other. This suggests that the distribution of matter in the universe is not the same everywhere, and the universe is full of these giant galactic filaments and cosmic voids. However, our standard cosmological models do not support the existence of such massive voids and cosmic structures. This is a serious problem with our cosmological model, and the new discoveries from the Webb telescope make it even more difficult for the standard model to survive. However, to explain all these mysteries, scientists have recently proposed a new model of the universe named Timescape.
Va šitas pavadinimas, Timescape, aš vis pamirštu. Jo, Timescape.
Cosmology. In this model, scientists highlight the significant influence of massive cosmic voids and structures.
Kaip suprantu, pagrindinis dalykas, kad, mes žinom, kad laikas eina skirtingai, priklausomai kur esi, kaip esi. Priklausomai nuo to, kaip greit keliauji lygtais, maždaug taip gal labiau, aš net nežinau kaip. Nes, kuo greičiau keliauji, to lėčiau laikas eina. Kad atrodo ten taip. Net ne. Kaip ten buvo, nes ir pagal gravitaciją, bet tai ir priklauso, žodžiu, nesvarbu, hugi visą šitą. Bet šitas Timescape, kaip suprantu teorija, kad tas laiko dilation, tas kaip skirtingai kaip laikas eina visiškai visur visatoje netolygiai pasiskirstęs. Tai tie voiduose laikas eina lėčiau lygtais jie ten teigia dabar, ar greičiau, aš nežinau, ir jis visur nėra statinis, kaip bebūtų, žodžiu, nežinau.
On the nature of time. They propose that time flows faster in regions of space with a high concentration of matter. For instance, an atomic clock situated
tame voide lėčiau tada eina pagal šitą. Vėlgi, aš žinau, čia AI video, man atrodo, aš nežinau, kiek čia teisybės ir ką jisai skaito iš tikro, bet pažiūrėsim keletą video.
Galaxy might tick up to a third slower, compared to an identical clock positioned in the middle of a vast empty void. Now think about this over the vast time scale of the universe. The universe is about 13.8 billion years old, but in regions with little matter, like cosmic voids, time has been passing faster. So billions of additional years may have passed in these voids compared to the matter-rich regions. This means that the universe doesn't have a single unified age as we often imagine. Instead, the age of the universe could vary depending on where you are. The age of the universe may be greater in the cosmic void than in a denser region of space. Here's where it gets even more fascinating. Since so much more time has passed in the voids, these regions have experienced more cosmological expansion. In simple terms, the universe has been stretching more in these less dense areas. If you're looking at an object on the far side of a void, it would appear to be moving away from you much faster than an object on the near side of the void. This is because the space within the void has expanded more over time. Now imagine this effect across the entire universe. Over time, the voids become a larger and larger part of the cosmos because they are expanding more rapidly. As a result, when we observe the universe, it creates the illusion that the overall expansion is accelerating. But in this model, there's no need to introduce dark energy. Instead, the faster expansion in the voids naturally accounts for what we see. In 2017, astronomers from the University of Canterbury in New Zealand tested timescape cosmology against observations and found that it was a slightly better fit than Lambda CDM to explain cosmic expansion.
Lambda CDM, tai man atrodo, čia tas dabartinis modelis, ta formulė, kur jie išrado CDM, ką reiškia? Cold Dark Matter. Lambda tai ar konstanta, ar kintamasis, ar kažkoks tipo tas koeficientas to expansiono, kaip plėtimosi. Ir, bet tam modeliui būtent to dark energy reikėjo, ar kažko to, tipo, kad paaiškint, kodėl plečias kažkaip ten. O tipo tas dabartinis naujas, tai nuo lambda to eina, nes nebereikia to dark energy. Ir tu vis tiek gali paaiškinti, tipo.
Expansion. What's even more fascinating is that scientists now suspect our Milky Way galaxy might actually be located within a cosmic void. Imagine floating in a vast, empty ocean where the closest sign of life is billions of light years away. This might sound like science fiction, but it could be our reality. For years, astronomers have wondered if our Milky Way galaxy is located near the center of an enormous cosmic void. But for decades, they were unsure about it. However, new images from the James Webb Space Telescope suggest that we are indeed inside a gigantic cosmic void. A recent research suggests that our Milky Way galaxy might actually be located in the center of a supervoid, an enormous empty region in space about 2 billion light-years across. Scientists believe that the presence of a supervoid could help solve one of the biggest mysteries in cosmology, the Hubble tension. Hubble tension refers to a puzzling problem where different methods of measuring the universe's expansion give different results. A new study led by scientists Sergei Mazurenko, Indranil Banik, Pavel Krupa, and Moritz Haselbauer tries to address this problem. They looked at something called the Keenan-Barger-Cowie, or KBC supervoid, a massive region in space that has fewer galaxies than usual, extending up to 300 million parsecs. This area is a sort of cosmic void, and it creates a unique problem for the standard model of the universe. However, observations of the KBC supervoid don't match what this model predicts. The researchers focused on two main issues, the Hubble tension and something...
Researcheriai. Va kaip fokusuojas ir kosmosą tyria. Ne, čia stock footage turbūt kažkokius tos naudoja, ne? Ar iš filmo, ten yra parašyta.
The researchers focused on
Gorodenkov, čia kažkieno animacija tiesiog.
Two main issues, the Hubble tension and something called bulk flow. Bulk flow refers to the movement of galaxies through space. According to the standard model, galaxies should move at certain speeds. However, new observations show that galaxies in certain areas, especially those near the KBC supervoid, are moving much faster than expected. These fast movements are surprising and do not fit well with the current model of the universe. To solve these problems, the researchers used a new approach. They applied a mathematical model developed by one of the authors, Moritz Hasselbauer, to predict how galaxies should move in the universe if this model is correct. Their findings suggest that if we consider this new model, the discrepancies between the observed speeds of galaxies and the predictions of the lambda CDM model can be explained. In simpler terms, they found a way to make the observations fit better with what we expect to see. Their new model suggested that the Milky Way may exist at the center of a supervoid, like KBC supervoid. Researchers said, if our Milky Way galaxy is living inside a supervoid, you're going to see things being pulled away from you towards the more dense regions of the universe. So if you're sitting in this void, your surroundings expand faster than the rest of the universe. From this vantage point, observers would calculate a higher rate of expansion compared to what they find in the distant, early universe, like they do now. What we understand so far is that the timescape model of the universe provides insights into how massive cosmic structures and vast cosmic voids can explain the universe's mysteries, all with...
Ok, dabar man reikia RPB Space įdėjo reasonable video, aš mačiau, kad tikrai yra 16 minučių ir ką Sabina įdėjo, mačiau jinai, kaip jinai, blet, Sabrina Has. Kaip jin, blet, yra? Palaš, gal šitas? Gal aš turiu išsaugojęs? Nes aš tikrai išsaugojau vieną kažkur. Jo, va, Sabinos. Sabina Hosenfelder, blet, kaip prisimint man jos tą, tai jo, aš mačiau, kai jie kalba lygtais tą temą, bet pažiūrėjau vidurį tipo, lygtais tą temą. Tai jo, aš noriu pažiūrėti, ką jie kalbės, bet turbūt šito nežiūrėsiu, nes tiesiog per ilgas, bet šiaip PBS Space gan išsameu paaiškina dažniausiai.
In 2011, the Nobel Prize in Physics was awarded for the discovery of the accelerating expansion of the universe through observations of distant supernovae that's usually attributed to dark energy. In a paper that just appeared, a group of astrophysicists from the University of Canterbury, New Zealand, questions the Nobel...
Beje, koks tas paper, kur appeared, man atrodo, gal man įdomu...
Found that I've covered...
Pala. Aš lygtai čia turiu... Blet, kaip daug klaidų padariau. Ar čia yra duoj numeris? Tai... Ar bus įdomu? Kaip atrodo tas... Blet. O galima tą paper kažkur actually rasti dabar, nes čia labai... Kur jinai rado tą? Okay. As featured in YouTube. SS Journal Love for Serious, tai jie čia tiesiog kalbėjo apie tai, bet pats šitas... Va, jis ir yra, kaip jis atrodo. Galaxies in the abstractus in the early universe appear to have grown too big too fast, assembling into massive monolithic objects more rapidly than anticipated in the hierarchical lambda called dark matter ACDM structure formation paradigm. The available photometric data are consistent with there being a population of massive galaxies that form early and quench rapidly over a short timescale, consistent with the traditional picture for the evolution of the giant elliptical galaxies. Similarly, kinematic observations as a function of redshift shows that massive spiral and their scaling relations spirals and their scaling relations were in place at early times. Nežinau, ką jie čia kalba. Explaining the early emergence of massive galaxies require either an extremely efficient conversion of baryons into stars or a more rapid assembly of baryons than anticipated in ACDM. The latter possibility was explicitly predicted in advance by modified Newtonian dynamics, MOND. We discussed some of our predictions of MOND, such as the early emergence of clusters of galaxies and early... Okay, tai čia tas tyrimas realiai bando išspręsti problemą, kodėl jie randa tų visokių struktūrų, kuriam tiesiog nebuvo laiko susikurti čia ir kaip atrodo šitas tyrimas sėkmės, žodžiu, supratau.
Prize-winning finding. The discovery that our universe is not only expanding, but that the expansion is speeding up has no simple explanation. There's no normal type of energy or matter that can make it happen. It requires a substance with negative pressure, a property that we've never otherwise observed, that indeed we have difficulties even interpreting. Physicists have just called whatever is causing this accelerated expansion dark energy. The simplest type of dark energy is one that's constant both in space and in time. It's then called the cosmological constant, usually denoted lambda. It's become one of the key parameters in the standard model of cosmology, the lambda CDM model, where CDM stands for cold dark matter. The authors of the new paper boldly assert that this is just the wrong model for the universe and that the evidence requires a foundational change to cosmological model. They say that if one uses the correct model, we do not need dark energy at all, not even in form of a cosmological constant. Their argument goes like this. Because there is a lot of matter in the universe, in practice we can't do calculations with the exact distribution of stars and galaxies that we observe. There are just too many. Therefore, for lambda CDM, we make a big simplification. We say that if we average over sufficiently large distances, then stars and galaxies have the same distribution everywhere. This idea is called the cosmological principle. It gives rise to the lambda CDM model that requires dark energy. But strictly speaking, this model is, of course, wrong. Galaxies and galaxy clusters are not uniformly distributed. Instead, it has patches with many galaxies in them, such as the one that we find ourselves in, but then there are big voids.
O jinai atsako priešingai, tipo, kad mes esam tame, kur daug galaktikų yra. Prieš tai tas AI video, tai kad mes voide galbūt gyvenam.
In between. It's not uniform, but more like an expanding sourdough starter, if you can imagine a sourdough starter that's several billion light years wide and made of galaxies. This is what the authors of the new paper looked at, a universe that has matter-filled regions like our own and voids. And all these regions do their own thing. They push and pull on each other. The authors call it the timescape model, because time runs slightly differently in each of these regions, but I think they should have gone with sourdough, because I'm sure that after you've forgotten everything I told you today, you'll still remember the sourdough. They say that the idea that the universe undergoes an accelerated expansion as a whole is a misinterpretation of what we observe in our vicinity. It's much like that what you observe in your home city may be a poor description for what happens in the world on average. But if we're careful and use the timescape model, we can then reconcile the supernovae observations with a normally expanded universe without the need for dark energy. To reach this conclusion, the group compared how well the lambda CDM model and the timescape model fit to a catalogue of supernovae observations. The authors use a Bayesian analysis, which quantifies the probability of a model to be correct, and find very strong to strong evidence for the timescape model in the low redshift regime that's in our vicinity. This agrees with earlier findings which have built up for some time that draw the cosmological principle which underlies lambda CDM, and with that the discovery of dark energy, into question. For several decades now, astrophysicists have found structures in the
Damn.
universe that are too large to be compatible.
Lemba, aš laukiu ilgai, kol galų gale tas James Webb teleskopas kažką tokio atras, kur kažką tiesiog pastums ir dabar panašu, kad tiesiog visas tas modelis ir, čia nėra gal visiškai nauji dalykai, bet, dabar jau turi įrodymų, va tokių, kad tas modelis biškai, žinokit, geriau veikia ir, į naują tą mąstymą eisim ir dabar, tipo, galimybių daug atsiranda, ką išmastys dar ir ką tada galbūt vėl tikrins, nepatikrins. Bet jo, pretty exciting, kai nieko nėra, tada 20 ten kiek metų stato teleskopą, jį paleidžia, per 1000 stebuklų jisai veikia ir keliauja kur reikia ir viskas gerai su jo iš esmės ir tada pradeda duomenys eiti ir tada kažką atranda pala. Kažkaip čia ne taip mes tikėjomės ir tada turi adaptuotis ir žiūrėti, kaip kitaip paaiškinti ir iš to ateina tas žinojimas po truputį.
Compatible with the cosmological principle. Since 2003, astrophysicists have known the Great Wall, a collection of galaxies about 1 billion light years away from us that extends over 1.5 billion light years. Then there is the huge quasar group, which spans 4 billion light years, and also the recently discovered Big Ring that spans 1 billion light years. According to lambda CDM, these large structures should not exist. And yet they do. By the way, this video comes with a quiz that'll help you remember what we talked about. What are we to make of this? While I'm sympathetic to the idea of the timescape universe and think it might well be correct, I also think it's too early to declare the end of dark energy. For one thing, analyses like the one in the new
No, it's not. RIP dark energy. We hardly knew it. Newer.
Paper depend a lot on their assumptions and the entirety of data
Timescape
used.
lame,
And I'd not be surprised if soon another group claims that lambda CDM is superior after all. Another problem I see with the timescape model is that even though the equations which they used in the new paper have the same number of parameters as lambda CDM, the full model is significantly more complicated than lambda CDM. Using the model would require a steep learning curve for astrophysicists, and that makes me suspect that its adoption will be slow. I'm not saying that this is good, I'm just saying it's what I expect, not least because the authors made a similar claim already 7 years ago and no one paid much attention to that either. As they say, all models are wrong, but some are useful, and whatever your misgivings are about dark energy, it certainly has proved to be useful for explaining our observations. And also, you have to admit that it just sounds very cool. To me, science is more than a profession. It's a way to understand the world.
Ja,
And
brilliant. Okay. Ble, čia 16 minučių mes jau nusidėsim.
Is expanding, and that expansion is accelerating under the
Na, aš turiu įsidėjęs, jo, prieš miegą pažiūrėsiu, bet nežiūrėsiu gerai. Man atrodo tiek čia tiesiog trumpai labai Timescapes naujas modelis, galimai keičiantis senąjį modelį, kaip mes visatą suprantam ir jos plėtimas, žodžiu. Koks vakaras ilgas, kaip širdim man gelia. Nuskink man jazminą.